Hello and welcome to the Space Telescope Public Lecture Series. Our talk tonight, Hearing the Light, how Sonification deepens our understanding of the cosmos and makes astronomy more accessible. I am your host, Dr. Frank Summers of the Space Telescope Science Institute, and our public lecture series has been online only for about 6 months now, and it will continue to be online only until further notice. That is due to our amazing tech team, Thomas Marufu and Grant Justice, who take these images and get them out to you on the internet. Upcoming in December, we will have Shaping Galaxies with Supermassive Black Hole Winds by Mitchell Rowalski. And in January, note the special date in January, January 19th. We're avoiding New Year's Day, and we're also avoiding the American Astronomical Society meeting, which is in early January. It's actually a little later than it usually is, so we're all the way down to January 19th, okay? We're usually the first Tuesday, but now we're down to January 19th for when we're doing this. But you're not going to want to miss that one because that is The Darkest Secrets of the Universe by Rajagopal at UC Santa Cruz. He's a wonderful guy. I've known him for many years. You're going to want to see that one. In February, we will have it on Groundhog Day, February 2nd, and it will be a fascinating topic by an amazing speaker that I have yet to schedule. All right, let's see. If you want to find out all the information, you go to our website, www.stsci.edu/public lectures. We'll find this webpage. You can see that there's the links to the webcast. There's also the link for you to subscribe to our emails and get our monthly announcements. Also on that page are a list of the upcoming lectures if you've forgotten what's coming up next month, as well as each one of those lectures has all sorts of details about the speaker and the topic, as well as after it has gone through, you can see we have the link to the webcast on the STSCI webcasting site, as well as the link to the webcast on YouTube. Our email announcements, as I said, the easiest thing to do is just sign up at the website. You can also subscribe to our YouTube channel, because all of these lectures are being posted to YouTube, youtube.com/Hubble Space Telescope, all one word. If you subscribe to that, you'll get notices of our new videos and reminders of live events like this. And finally, if you have comments or questions, you can send them to publiclecture@stsci.edu. Our social media, we've got social media for the Hubble Space Telescope, for the James Webb Space Telescope, which launches less than 1 year away. We're 1 year away from launch of the James Webb Space Telescope. We're excited about that. We also have social media for just our institute, Space Telescope Science Institute, Facebook, Twitter, YouTube, and Instagram as listed there. Myself, I only do a tiny amount of social media. I'm going to do a little bit on Facebook and a little bit on Twitter. You won't be inundated if you follow me. You'll just get things every now and then. Okay. So now our news from the universe for November 2020. Our first story tonight, getting the big picture. And we mean big picture. All right. So there's a new observatory going in Chile, up on the Sierra Tololo in Chile. This is the Rubin Observatory, named after the astronomer Vera Rubin. And this is an image of it as it existed, as it was in May of this year. And it's progressing really well. They will start data taking sometime next year, and they'll actually move into operational in 2022, I believe. Now, this has got a huge mirror in it, okay? This is the mirror blank before it was illuminized to have its reflective surface. It's an 8 meters across. This image just shows you just how huge this mirror is. You can do that in a ground-based telescope. And with a mirror this big, you also need to have a big detector. Well, they have one, and it's called LSST CAM. All right, and this is a combination of many, many CCDs put together at the prime focus of the Rubin telescope. And it's just an amazing new detector. Okay, so here's some characteristics of LSST CAM. First of all, the field of view is 7 full moons across. Okay, it's 40 full moons across the whole detector. That is huge. There is a huge field of view, but it also has incredible resolution. As you can see on the right, they've got this picture where you can't really see, is there a golf course in there somewhere? Yes, there is, obviously, and they can actually resolve the golf ball on the golf course. They say they can see a golf ball from 15 miles away. All right. Now, it's great resolution, especially for ground-based, but ground-based does have its limits. Hubble has 4 times better resolution than LSST can, but hey, Hubble's in space. Hubble doesn't have the atmosphere to look through, so it does amazing things. It's going to be huge, and so this detector that I showed you is now operational, and they wanted to test it. So they did a pinhole camera to just test it. And this is one of their test images. 3.2 billion pixels, 3.2 gigapixels, right? I mean, you may be impressed that your phone has, we used to be impressed that our phones had 1 megapixel or 5 megapixel, now 10 megapixel, 40 megapixel. No, 3.2 gigapixels here. Okay, this image that they use to test it is actually Vera Rubin processing some of her data, and they took that image. They use a pinhole camera to spread it out across the entire thing to get a test image. All right, and so they now are beginning to characterize the detector. They're being able to figure out all of the various details of it, and showing that they really do have 3.2 billion pixels to work with. And this really, it made me sort of think about, wow, where are we going to go in the next decade? All right, so this is a Hubble image, right? This is a Hubble image of stars in the Andromeda galaxy. And there's so much detail in a Hubble image. But as you can see on the right, that's a tiny, tiny region in the halo of the Andromeda galaxy, okay? For Hubble to see the entire galaxy, it would be really, really difficult. But we tried. We actually did make a Hubble mosaic called the Panchromatic Hubble Andromeda Treasury Program, or the FAT program. And at Orange Square, that's one Hubble detector. And we had to take like 300 images to cover basically about 1/3 of the Andromeda galaxy, as you see on the right. So Hubble has been able to cover that much. And if you came to our previous talks about what used to be called the WFIRST, is now the Roman Space Telescope, you can see that learned that the Roman telescope has 18 different detectors spread out over a much larger region, and that Roman, as shown on the right, can do all that Hubble did in its 300 or so pointings in like 2 or 3 pointings. So Roman will have a huge field of view. But even that is not the same as what Rubin will have, because when we compare Roman to Rubin, Rubin will be able to get the entire Andromeda galaxy in one image. Wow, that's what we're going to get. We're going to go from, these 16 megapixels images from Hubble, and we put them all together to make them even bigger, but we're going to get 3.2 billion pixels with every image from the Rubin telescope. We're going to have a smorgasbord of data over the next decade. Our second story tonight, it's the Greater Pumpkin, Edwin Hubble. Okay, all right. So we have a lot of international viewers, and they may not get the reference. In the United States, we have a tradition of a Halloween program called It's the Great Pumpkin, Charlie Brown. I think Peanuts is probably worldwide, but this TV program came out in 1966. And our news chief decided, well, we got to have some sort of tie-in for Halloween. So we found an image and it sort of looks like a pumpkin. And here is that image. These are the interacting galaxies NGC 2292 and 2293. What you've got going on here is those white eyes. Those are the cores of the galaxies that are mixing together. And all the other material around it is the galaxies as they've smashed together and are now mixing it up. And down bottom, you see the dark dust lane. Okay, that dust lane, there's a little bit of star formation going on this lane. That sort of forms the smile of the jack-o'-lantern. Okay, and when they found this, they said, all right, we got to do this for a Halloween release, and it looks sort of like a pumpkin, so we'll call it the Greater Pumpkin. I actually think it looks a little bit more like Jack Skellington from The Nightmare Before Christmas. But I guess making the Jack Skellington reference isn't the same, although he is the Pumpkin King. But that was our Halloween release to show off the interacting galaxies and how cool they can look. All right, we have one more story for you, and it's a really special one. We are celebrating a century of cosmic inquisitivity. Now, I've been doing the public lecture series for almost 20 years now. 19 years I have been hosting it. And most of my time that I've been hosting it, I have seen one particular member of the audience down in the front row. And she has just turned 100 years old. So we are going to shout out to Molly Whittow from Baltimore, Maryland, who is 100 years young this month. Okay, Molly is amazing. She comes to the public lecture series when we're able to have it in person, and she sits in and she's always got inquisitive questions. She's told me that she's gone and seen several solar eclipses over her life. And so I was going to sing for you guys, but you know, you really don't want that. I'm not a singer, but I am a visualizer. So Molly, for your birthday, we have an observation of the birthday cake nebula visualized just for you. Happy birthday, Molly. Everybody, go to the chat on YouTube and type in your happy birthday congratulations from Molly, who is 100 years old this month. All right. Let's get back to our regularly scheduled program, Hearing the Light, how sonification deepens our understanding of the cosmos and makes astronomy more accessible. I'm going to stop my screen share while I introduce the speakers. So we have Scott Fleming, Clara Brasseur, and Jen Kotler, who are going to be speaking here tonight. Scott is a senior astronomical data science working in the MAST archive. That is the Mikulski Archive for Space Telescopes. It's where we keep all the data from both Hubble and lots of other space telescopes. He received his PhD in astronomy from the University of Florida in 2011. And his research interests are in exoplanets and stellar astrophysics. Our second speaker is Clara Brasseur. She is a senior software engineer at the Space Telescope Science Institute. She primarily builds Python tools for astronomical data access and also performs research on stellar flares. Our third speaker tonight is Jen Kotler. She leads user experience design at the MAST archive. She is passionate about using design and open technology to make science accessible to everyone. And these three wonderful people have collaborated on this really amazing project. And so I will turn it over to you. Scott, you are speaking first, right? Ladies and gentlemen, Scott Fleming.
Yes, that's right. We'll have to let's get the slides up here. Welcome everyone. Welcome everyone who is watching the archive on YouTube, and an extra special welcome to all of you attending the live stream. I'm really excited to give a talk today about our work on sonifying astronomical data. This is going to be a team presentation. So I'm Dr. Scott Fleming. I'm here with two other team members on the Astronify team, Clara and Jen. going to pause and let them introduce themselves, starting with Clara.
Hi, I'm Clara Brasseur. I'm the lead developer on this project. So I have been running all the software that we're used to make all of the sounds that you'll be hearing throughout this presentation.
Hey, guys, kill the screen share if you're going to be introducing yourselves.
And hi, I'm Jen Kotler, and I'm, as I mentioned, a user experience designer. So I'm focusing on the usability and doing testing for all the sonifications that you'll hear today, and also working on some outreach exhibits to try to share this with a wider audience.
All right, so we'll get the slides back up, and the talk will be in 3 parts. I'm going to first do an introduction and a background on the project and about sonification. Clara is going to show you some astrophysical examples of sonified data, and then hopefully the best part, Jen will walk us through a game show where you'll be able to try to test your ears and see if you can hear the sonified data and signals from some of these astrophysical objects that we're turning into sound. So before I begin, one more important point. This is going to feature a lot of sound, unlike some of the other presentations. And so if you do have some headphones or the ability to turn up your volume a little bit, you may want to do so you can hear the sounds as well as possible. Okay, so I already introduced myself, and I'm the principal investigator and the lead scientist, lead astronomer on the team. Jen is the lead designer. Clara is the lead software programmer. And then Kate Meredith from Glass Education is our education and outreach specialist and is a very important part of our team here. Okay. So I want to first talk about what sonification is, because it's probably a term that not a lot of you have heard before. And I want to start off by telling you what sonification is not. So what sonification is not is it's not sounds themselves. So for example, ocean scientists use something called hydrophones. You see a picture of one on the upper left. It's basically a very sensitive microphone that they put under the water and record sounds to study what they are and what's making them. So some examples might be a distant ship, it could be whale songs, it could be dolphin communication, it could be undersea earthquakes and volcanoes, but they are recording sounds to analyze. In other words, the sounds are the data. But when we talk about sonification, what we're really doing is we're representing other types of data as sound. And you're already used to this from a visual perspective. We've all seen things like bar charts and pie charts and trend lines and weather maps. So these are all ways that you can represent things like how hot it is outside, or what the stock prices are doing, or how many products a certain person may have bought in a store as graphs or maps. And in our case, what we're doing is representing other types of data as sound instead of these more visual methods. And that is what sonification is. So why do we want to do this? Why do we want to sonify data in the first place? There's 3 main important points for sonifying data. The first one is about sensitivity. So it turns out that most human ears can distinguish something like 1,300 different frequencies. And the human ear is very sensitive. The human ear can actually detect changes of sound at the microsecond level. That's 1/1,000,000th of a second. And if you're a fan of video games or movies like I am, visually, you'll know that a lot of monitors and television screens typically are what we call 60 FPS, frames per second, or maybe the top of the line ones are trying to go out to 120 frames per second. But it's something like about 100 frames per second. And there's a reason why companies haven't bothered making 1,000 frame per second monitors or 1,000,000 frame, because the human eye just can't see it, it turns out. So visually, we're sensitive to things at like the 100 frames per second level, but audio-wise, our ears can detect things changing at a much higher resolution. There's another reason why sonification can be a benefit, and it gives you another way of analyzing data besides visually. So in particular, sonifying data allows us to do what we call multidimensional analysis or multidimensional, sort of preview of the data. And what I mean by multiple dimensions, I'll go through real quick with some examples. So if I asked you to make a chart of a baby and how it's growing in its weight over time, you can do that. You could measure the weight and make a chart. You probably have seen these in doctors' offices. Some of you may even do this at home. It's not too hard to do. We have the age on the horizontal axis. We have the weight on the vertical axis. Not a problem. Now, if I ask you though to go ahead and try and do that, and I want to see how the weight and the height sort of correlate with age, now we have to make a three-dimensional plot. And that's a little harder to do, but with computer graphics, we're able to do that. But if I then go ahead and ask you to now see how the weight and the height and the temperature and the O2 level and your vitamin Ds and your blood pressure and all these things are all correlated together, we run out of options, right? Because we can only visualize a three-dimensional space on a 2D surface like a screen or a piece of paper. So there are tricks you can try to do where you represent all these different variables using different visual cues, like different colors for one thing and different sizes for another thing, and different, whether it's filled in or not, and you play with the X and Y and the Z axes, but pretty quickly the chart becomes too complicated to see a lot of detail. One of the cool things about sound is that it's inherently multidimensional. And if anybody has played around with 3D sound or have surround sound systems, you kind of know this pretty well, because you have not only the concept of, if you have good speakers, left and right, up and down, front and back, but also things like the volume of the sound can be changed and the type of sound itself can be changed, whether it's different instruments, or you can change different pitches and different tones and overtones. And we immediately have all these extra things to be able to assign to variables to be able to explore our data set from an audio perspective. And the third and most important reason is accessibility. So for people who are blind or low vision, the only way that they can really interact with data is primarily through audio or touch. And astronomy in particular, as well as science in general, is oftentimes such a visual visual subject, where images and graphs and all these things are dominant in our field. And so providing data through a sonified format increases the accessibility of data to these to community scientists who are interested in participating in things like citizen science projects, and also for those who want to do astronomy as a career. So those are our motivations for the project, and I'm going to take you through a couple simple examples using shapes, because shapes are something we all understand, and then I'm going to pass it off to Clara, who will get into this astrophysics part. So this is sort of to calibrate our understanding of what we mean by sonification. And as a quick note, because of the video and audio lag, there might be a little bit of a difference between the sound you're hearing and where the red marker is, but don't worry about it. If you're curious, you can always go to our homepage and click on the YouTube videos for some of these and get a good sync. But we'll continue. So to get everybody on the 0 point, what I'm going to play right now is the simplest possible use case, which is nothing changing. So let's listen to what that might be. Constant, steady tone, because we have constant, steady shape. Okay, that's pretty good to understand. Let's change it a little bit now. And what we're going to do is we're going to draw a diagonal straight line, roughly at a 45-degree angle. And we'll see what happens when we sonify the shape. All right, so now you can really hear that things are changing. This, just like the line or the shape itself is changing, the sound you're hearing in pitch is going from low and constantly going up to a higher and higher pitch at the end. Now let's look at what we might expect for the top of a triangle. And I bet you all could figure out what this might sound like. Let's go ahead and listen to this too. All right, so that sounds just like we might expect it based on either the shape or the graph. We have essentially two diagonal lines, one going up, one going down, and just like the shape itself, the sound is literally rising and falling constantly and pretty sharp. So the very last thing I want to present is what the top of a circle might sound like. Let's go ahead and listen to that. So just like the triangle and just like the shape, the circle is also rising and falling. But the shape itself, if you think about a triangle compared to a circle, it's a much more gradual and constant change, much more gradual change from one side of the circle to the top and to the other side of the circle. And just like that, you should have heard the sound compared to the triangle also change in pitch much more gradually until it reaches the top and then gradually fall down. As opposed to the triangle, which had much quicker changes in pitch when it got to the top and then went back down again. So this is just to show you what we mean by sonifying data. In this case, it's shapes. But for the next part of the presentation, Clara is going to go through some examples of how we take astronomical data. This is real measurements. In our case, real measurements of the brightness of objects, and we'll translate those measurements into sound. Claire, over to you.
Hi, everyone. So I'm going to talk about, as Scott said, applying the techniques that we use to sonify those simple shapes and applying that to real astronomical data. Whoops. So to start off with, the kind of data that we're sonifying is called a light curve. So at the very introduction, there were all these beautiful pictures of galaxies and stars and even a birthday cake, and those are all images. This is a different kind of data. It's fundamentally a record of how bright an object is, a star or a galaxy or whatever astronomical object we're looking at is over time. Space Telescope holds data from two very important space telescope missions that produced light curves. They're TESS and Kepler, and both of them, their primary purpose has been to search for exoplanets, planets that orbit stars other than the sun. However, they both produce a lot of data about a lot of stars, and so we can use that data to look at a lot of different astrophysical phenomena, not just exoplanets. So the way we typically visualize light curves is as a line graph. Because it is a measure of the brightness of star over time, you really what you have is a data table that has two columns. One is time and one is how bright the star is. So we can plot that with time on the x-axis and light on the y-axis, and then we can just look at the line and see when it's higher, the star is brighter, and when it's dimmer, when it's lower, the star is dimmer. So when we translate that into sound, we keep time as time. We simply scale it to be something that's reasonable to listen to. And then instead of translating how bright the star is into the place on the plot, we translate it into the pitch. So just like Scott showed, the higher the pitch, the more light, and the lower the pitch, the less light. So this is a real piece of data from one star that came from the Kepler light curve, Kepler Space Telescope, and this is how it sounds. So this is pretty similar to what Scott was showing, but it's a little more complicated because this isn't a simple shape. This is the light from a star. So we can use this then to look at a lot of different things. So even though I said that we can look at a lot of different things, we're going to start with exoplanets because exoplanets are great. And exoplanets are the reason these telescopes were put into orbit and the reason that they were designed to return light curves. So when you're looking for exoplanets in light curves, what you're looking for is what we call a transit, which is when a planet crosses between the viewer, in this case us or the telescope, and the star that it's orbiting. So the star is putting out an amount of light, and then some of that light is blocked as the planet transits across it. And then when it finishes transiting across it and continues its orbit around the back, the light from the star is not blocked again. So we're looking for these characteristic dips in the light curve that occur at regular intervals as the star continues around and around its planet. So we've discovered that there are a lot of planets outside of our own solar system, just a lot of all different kinds, and many that are just very, very foreign to anything that we have in our solar system. And one of the ones that I think is particularly interesting are what are called hot Jupiters. So probably some of you have guessed that these are Jupiter-sized planets, but unlike our Jupiter, with orbits pretty far out from its sun, certainly farther out than we on Earth do, hot Jupiters orbit incredibly close to their host star, like closer than the orbit of Mercury if they were in our solar system. And Jupiter, our Jupiter, is made up of a lot of gas. And so these Jupiters are like that too. Their composition is more like Jupiter. So they're just huge and puffy and hot and very, very close to their host star. So Kepler 12b is a planet that was observed, unsurprisingly, by the Kepler Space Telescope. And it's a hot Jupiter that is orbiting a star that is very similar to our own sun. But obviously its system is very different from ours. It has a period of just 4.5 days. So that means the equivalent of a year on this planet is just 4.5 days. And knowing that, we can also get a sense of the time scale of this sonification here. So in this plot, there is this flattish line across the top is the light from the star that is blocked in these dips by the transiting exoplanet. And so the distance between these is going to be the length of the orbit of this planet. So this is 4.5 days. So we've sped it up so that it will actually play in just a couple of seconds, but that gives us a sense of scale. So let's hear what this sounds like. So we can hear this constant pitch that is the light from the sun interrupted by these lower chords that are the transit of the planet periodically. And this planet, but because it is so big and so close, it blocks out a lot of the light from its star. So these dips are very clear. The second type of star I'm going to talk about is called a heartbeat star. And it's called a heartbeat star, but it's actually a binary star system. And it consists of one star orbiting a larger star in an elliptical orbit. And so what that means is that there's a large star and a smaller star is orbiting in such a way where sometimes it's very close to that large star and sometimes it's very far away. And what the result of this is while the smaller star is much smaller, it isn't as small as a planet, and it still exerts it exerts a gravitational pull on the larger star enough to destabilize the star and essentially cause it to ring like a bell. So there's these ongoing vibrations in the larger star, and they are stronger when the stars are closer together and weaker when the stars are farther away. And the result of this is that the light curve, when plotted, looks a little bit like an EKG with the up and down. And so this is why it got the name heartbeat star, even though it's actually two stars. And so this is the plot, and we can see that behavior. These are the small up and downs that are the vibrations that are induced in the large star, and they get larger and smaller and larger and smaller on a fixed period, and that is the orbit of the star. And so if we sonify this such that we're scanning across it very quickly, we can hear that large scale orbiting pattern very easily, like this. So here, it does really feel in some ways like a beating pattern, so you can sort of feel that heartbeat. But you can't really distinguish the smaller scale changes. You just know that you're getting a large chord and then just a few notes and then a large chord. So you can hear that, but you can't hear the smaller up and down. So if we sonify again, but this time scan across much slower, we can start to hear those up and downs. So now it's a little bit harder to detect the larger scale pattern because it's so much slower, but we can really hear those vibrations. And so the way you sonify a piece of data, just like you make changes in how you visualize a piece of data, is based on what you're trying to explore, what features you're looking for, and what information you want to get out. So the next type of star we're going to look at is a pulsating star. And so this is a single star, and it's an star that expands and contracts regularly. These stars tend to be very hot. They are unstable. So inside the star, in with all of the hot plasma, there's some instabilities so that the star will puff up. It will get hotter and puff up, and then it won't be able to sustain itself. And so gravity will start to take over and it'll collapse back. And at a certain point, the compression of the plasma will cause it to stop and heat up more and expand again. And this just goes back and forth and back and forth. And so you have this in and out motion, and so that physical motion of the star translates to a corresponding change in the brightness. So in this case, when we sonify it, we're sort of inferring from an infer. So we're using sound to hear the differences in light, which is telling us about the changes in the physical size of the star. And these happen over short periods of a couple to days to maybe a little over a week, and they're very regular. So this is a heartbeat star. This is what's called a delta Scuti. So it's a young, hot, pulsating star. So it's very young and it's very hot and it's wobbling. And this is what it sounds like. And it just keeps going. We have years of this data, and it just keeps going, because on the scale at which we're taking data for these space telescopes, it is very constant. Even though it's an unstable star, it's unstable in a very stable way. It's going out to the same radius and shrinking to the same radius and continuing. But on astronomical scales, these stars are unstable, and so they're short-lived, and are some of the more active stars in terms of moving around their characteristics, but that's still on an astronomical scale. So it's much longer than a scale that we can see over the course of even a relatively long telescope mission like Kepler, which took data for 12 years. And so the last astronomical phenomena I'm going to talk about is different than the ones all of the ones I've talked about before, that all have some sort of regular period, whether it's because there's a planet rotating a star rotating another star, or a star pulsating. Stellar flares are surface explosions on stars. They're the stellar equivalent of solar flares. And they're a result of buildups of energy in the upper layers of the star and the atmosphere, and they build up slowly over time. And when a certain critical amount of energy is reached, it needs to go somewhere, and so it explodes very quickly in a burst of light and energy, and then collapses back into the star as it was before the explosion. And these aren't predictable. We know basically how many we expect to see of what energy over a long period of time, but we don't know when any individual one is going to happen. So instead of seeing something periodic, we see something more like this, where you have this baseline starlight, and then there's this sudden sharp peak, that's the flare, that then more gradually returns back to that baseline. And so here's a real flare from a space telescope. And it sounds really quite lovely. So this is a great flare because you can hear this sharp explosion. There's a sharp peak, and then it gradually returns. In fact, at the end of this set of data, it has not returned all the way back to the original amount of brightness. So that will continue. If we had more data, we'd get to see it. However, flares occur at a lot of different scales. They can be anything from a couple of minutes to a couple of hours in duration. So depending on how often we're taking measurements of the star, they could look like this one where we get to really see the whole shape. Or they could look more like this one, which is this large spike that just sort of pops out and then disappears, because this flare is very short compared to how often we are measuring how bright the star is. And so this light curve is also, it's got a lot of other things going on. There's some sort of periodicity. Maybe there's some star spots, which are cooler parts of the star that are therefore dimmer. And so when the star rotates, these cooler spots will rotate with it. And sometimes we're seeing them and sometimes we're not. So they have these smaller scale periodic variations as we see the total amount of brightness from the star change based on the temperature in various spots on the face of the star we're seeing. And so that's happening below these. This is definitely a flare. This little one looks like it's probably a flare, and this one, even this one could be. It's a little hard to tell because this is a slightly messier light curve. So let's see what it sounds like. So here, it's a little harder to hear the flares, and they're just like little high-pitched blips that come out because they're so fast. But we can see that they do stand out above this general activity that's going on in the non-flaring star. But if we did want to really dig into what's going on in the star without flares, well, we'd pick a part of the light curve where there aren't any, and then we would do what I did with the heartbeat star and slow it down and really zero in on what this activity is. So that was a brief introduction to various different kinds of astronomical phenomena that we can sonify. And now I'm going to hand off to Jen, who is going to play a game.
Hello, everyone. Welcome to the Astronify game show. I'm your host, Jen Kotler. So we've now arrived at the interactive portion of this lecture, where we're all going to act as astronomers working to discover information about the universe using our ears. So in true game show fashion, we have several ways to participate. Of course, the classic, you can just shout your answers at your screen. But when I say interactive, I mean that I want to hear from you. If you're watching this streaming live on YouTube, so November 10th, 2020, please find the chat. And as we go through each question, I want you to write what you think the answer is. And after each round, I'll check the chat to see how you're all doing. If you're watching this after the original stream, there will be a link added to a survey that will be added on top of the video and also in the description. If you can follow along and answer each of these questions in the survey as I go through them, I would greatly appreciate it. Hearing back from you is all interacting with us is really fun, but it's also really important, a really important learning experience for our team, because it's a great way for us to check in with a wide group of people and see if these sonifications are understandable. So it'll help us learn how to improve our work. Thank you to everyone who participates in advance. Okay, let's get started. So this game is going to have 2 rounds. Round 1 is flares. So remember what Clara said earlier about flares. They are explosions on the surface of stars. So first, I'm going to show you an idealized example of what a flare sounds like sonified. So keep in mind that short, sudden rise in pitch that has a slower decay at the end. That one was very ideal though, and now we're going to move on to real data, which might be a little bit more difficult. So in this round, I'm going to play 4 sonifications. After each sonification, I will ask you, did you hear a stellar flare? So if you're watching live, please write yes or no in the chat. And if you're not watching live, if you're watching later, can you please answer the question in the poll as we go along, in the survey, I mean, link in the description. Okay, so question 1, does this contain a flare, yes or no? Okay, what do you all think? Let's take a few seconds to give you a chance to write it in the chat, answer on the survey. Did you hear a flare? What do you think? Okay, I think we've given enough time. Let's find out. Yes, that was a flare. So you can see the arrow on the screen, and I'll also mention it as we pass it in this replay. There it was. Okay, so great job, everyone. Let's move on to the next question. Question 2, does this contain a flare? Yes or no? Okay, so let me give you a few seconds to write in the chat or respond in the survey. Yes or no, did you hear a flare there? There was certainly a lot of variation, but was it a flare? That's the question. Let's see if anyone's responding yet. Huh? Okay. And let's find out the answer. That one did not have a flare. So let's listen again, just to not hear the flare. Okay, so question 3, does this contain a flare? Yes or no? Okay, so are you listening closely? What did you hear? Was there a flare? What was going on with this one? I'm wondering if anyone heard anything unusual about this one. Maybe they could comment if they think it's different. Anything different about this than the previous sonifications? Okay, let's see. There was more than one flare. Not only was there one, there was many flares. Great job, everyone, for noticing that. So for question 4, we're going to re-listen to that previous sonification. And this time, I want you to count how many flares you hear. And this one is a little tricky because some of them are more subtle than others. So you have to listen really closely. Okay, so how many flares do you hear? Write the number in the chat or write the number in on the survey linked at the bottom. Okay, how many flares were there? So we know there's more than one, but how many exactly? Let's see. Oh, I see answers starting to come in. Okay. Give you another second to respond in the chat. And let's reveal the answer. There was 7 flares. And so I've marked them off so you can visually see them. And then as they pass along in the replay, I'll also make a verbal note of when they happen. 1, 2, 3, 4, 5, 6, 7. And so number 6, I think, is the most difficult to hear. And you can see visually it is the smallest out of all of them. So you have to be listening more closely to find that one. So I'm going to take a moment to go back through the chat and just see how everyone's doing, because it's a little bit delayed from what I'm seeing. I was seeing that I'm seeing a lot of close answers, a lot of 7s, some 6s, which I think is understandable on that previous question. Okay, you all did see that there was many flares. That's awesome. You're all doing great. I think you get a million bazillion points. Congratulations. We can move on to level 2, round 2, exoplanets. Okay, so remember what Clara said earlier. Exoplanets are planets that are in other solar systems, and they transit when they cross in front of their host star and block some of the light. So first, I want to show you this idealized example of what a transit sounds like. And we heard some earlier. This one's a little bit more drawn out so you could hear the detail. And what a transit sounds like, as a reminder, is it starts at a high pitch, it deepens as the planet transits in front, and then it returns to the original pitch. Okay, so that's what an idealized example of a transit sounds like. So in this round, I'm going to play 4 sonifications. After each sonification, I'll ask you how many times you heard the exoplanet transit. So this is a counting one again, very similar to the final question in the flares. If you're watching live, please write the number in the chat so I could see how you're doing. And if you're watching this archive later on YouTube, click the link below and start sharing your responses with us in the survey. Okay, so question 1, how many transits do you count? Write in the chat or respond in the survey link. What did you all think? How many did you count? Okay, I'll give you a few seconds to respond before we reveal the answer. Okay, let's see if any chats are coming in yet. Well, I think it's time to move forward. Let's reveal it. How many transits were there? 5. There was 5 transits, and I'll make note verbally as we pass through each one on the replay. 1, 2, 3, 4, 5. And so you can hear that really clear dip as the transit happens. Okay, let's move on to the next question. Oh, and I see a lot of you are getting that one right, so that's awesome. Okay, once again, how many transits do you count? Okay, what do you think? How many transits were there? Let me give you a few seconds to write that in the chat or respond in your survey. And let's reveal it. How many were there? There was 19 transits. So I'm going to play it again. I'm not going to count as each one, but you'll hear a repeating beat almost as at a very regular cadence as the planet transits in front of the star. Okay. Yeah, and I see the answers coming in now. A lot of you heard 19, so fantastic job. An extra 1,000,000 points to you all. Okay, question 3. How many transits do you count? Ooh, I heard a little extra something at the end of that one. How many transits do you count? Let's give you a few seconds to respond. Remember, in the chat or in the survey linked below. Okay, let's find out. There was 3 transits, and I think some of you might have heard that little extra flare at the end, which you can see visually on the right-hand side of the screen. So I'll point out these 3 transits in the flare as it goes on. 1, 2, 3, and there was a little flare at the end, the high-pitched blip. Okay. Seems like a lot of you are saying 3. It's awesome. Okay, so this is the final question, and I want to warn you all, this final light curve is a real challenge. It is a lot more difficult than the others, and I even have trouble hearing it, and I'm working with this data quite a lot. So make sure to listen really closely. So here we go. How many transits do you hear? How many transits did you hear? What do you think? That's a tough one. And so I'm actually going to try to replay this one once more, just to give you a second chance to listen before responding. So, okay, on that second listen, were you able to hear it? It's pretty tough. Okay, so I'm seeing some numbers come in. Let's reveal, what is the answer? So there was 3 transits, and I want to explain what's going on with this star. You can kind of visually see where they are, and they're not all at the lowest dip in this light curve. So the baseline light coming from the star has its own undulating up and down pattern in addition to the transit. It's possibly caused by something like star spots, which are areas with more or less light. So as the star spins on its axis, the sonification is representing this up and down pattern of the brighter and dimmer areas. As the star is spinning, the star spot might pass and deepen or brighten the light. And so this is happening regularly. And in addition, a planet is also transiting in front. So this sonification is a really great example about how studying data in multimodal ways can enhance our understanding. Because in some cases, audio draws our attention to qualities we couldn't see in a graph. But in others, it's easier to see it than to hear. So there's a place for sonification and a place for visualization, but most powerfully is when we combine the two. So I'm going to take a look at the chat and see if anyone got that last one. Let's see. I saw some people got 3. A lot of people thought 4. Okay, I bet you were hearing the undulation, the overall star's brightness. Okay, awesome. So let's move on past this. I hope you all enjoyed playing. Oh, I forgot to replay it. There's the second one. Okay, so for me, I'm clearly able to hear the second one, but it's hard for me to hear the first and second. So here, let's play it one more time, just to listen again. Okay, so there you are. That one was a pretty tough one. I really hope you enjoyed playing this game. And if you like listening to data and answering questions like these, I encourage you to go to our website, which is Astronify, ASTRONIFY.readthedocs.io. And if you scroll down, there's a games section. Level 1 is very similar to what you just did, the exercise you just played. But level 2 is a totally different one. And it focuses on exoplanets and dives deeper into ways you can listen and analyze transiting exoplanet data. And at the end, you'll find out what the correct and incorrect answers were and how you did. So, and once again, these survey results really give us fantastic feedback, and we can help learn how to improve the sonification. So thank you for doing that. And finally, just want to quickly tell you about this other part of our project, which are these interactive exhibits. Main goal of this project has been to bring astronomy and sonification to a wider audience. And to that end, we're working on 3 interactive sculptures that we could show at local events. And we also want to bring them on the road to classrooms and conferences. And as with the rest of our project, we want to make sure these exhibits are accessible to blind and low vision people. We are so excited to be working with Bill Haas, who is a museum exhibit designer extraordinaire. This guy can build anything. His day job is actually designing museum exhibits for the Smithsonian Air and Space Museum in DC. So we're so excited to be working with him. Unfortunately, COVID happened. What a drag. It's pretty awful. But so we've kind of slowed down the process for these in-person exhibits because clearly gatherings of people who are all touching the same sculptures is no longer advisable at this moment in time. But we're still making some progress and we are excited to do more with this in the future. So this image that we're showing on the slide is an in-progress sculpture, and it's the exhibit I'm most excited about. It's a light curve xylophone. The instrument is built in the shape of a light curve, and as you play the instrument, you run your hand along the shape, which is a great way to physically understand the shape of a light curve. And then as you're making the noise, it's actually creating music in the sound that we would sonify. So higher pitch for more light, lower pitch for less light. So it's in progress and the sounds still need a little bit of tweaking, but I can't tell you how excited I am about this sculpture. And I have a short video to show you, to give you a sense of how it will work. Okay, so that's that portion of the project. If you're excited about the things you've been hearing in this presentation, I want to invite you to join us. Astronify is a Python package that we built to sonify our data. And by we, I mean Clara. Clara has built it mostly by herself. Very impressive. So it is open source and you could find it on GitHub. And if you're familiar with Python coding, I encourage you to try installing it and to sonify your own data. We also welcome contributions if that's something you're into. And also, if you're just generally interested in this project, excited about sonification in space, whether you code or not, I encourage you to check out our website and join our mailing list so you can listen to more sonifications, hear about project updates, and future events like this one. Once again, the website is Astronify, astronify.readthedocs.io. Thank you all so much for tuning into this presentation. We are very excited to answer whatever questions you may have. So thank you.
All right. Thank you very much, Jen. That was really, really a lot of fun. I was watching the chat and everybody seemed to have a blast playing this little game show to go along with it. So this is one of the first times we've done this at the public lecture series, not only given them information, but actually let them utilize that information. So thank you all for a wonderful presentation. And one of the questions that somebody asked on there was the same question I had was, just can we get an idea of what inspired you to do this sonification? Were there other projects that you saw that that pulled you into this? You know, I'd like to hear from each one of you as to, you know, what brought you into this? What pulled you into this idea?
Yeah, I'd like to have maybe Jen and then Clara, and then I'll if I have time, I'll go through the inspiration for me. So maybe Jen, do you want to say something about what inspires you to work on the project?
Yeah, I mean, so I come from an art background. I have a bit of an untraditional background for working at Space Telescope Science Institute, where it's mostly people who are developers and scientists. And so I'm really excited about the idea of trying to create art with data and, you know, different ways of visualizing data. And it's been something I've been thinking about. And we had this great public lecture by this fellow named Gary Foran, who is a PhD candidate in Swinburne, I believe, in Australia. And he came in to talk to us about the project he's working on because he's actually blind and he's working on his physics degree. And so he's working on studying data, but I think he was struggling. He was probably needing people to verbally describe what they were seeing on charts and graphs. And so he and a few other people are working together on sonification, and he gave a talk about all the promise that it has, and he played some sonifications. And I was just really excited and inspired to hear this. And I mean, both from the accessibility standard, of course, but also just imagining the art and the interactivity, and it's such an amazing way of putting you inside data. So that's what inspired me.
All right, Clara, you have anything to add?
Yeah, so I I mean, I do have a physics background and I work at Space Telescope, but I also have a music composition background. And so data sonification, when, I learned about it as a thing, it was something that I was very interested in. And I've done some sort of electronic music in the past. And so is very, I used to use random numbers and things as inspiration. So it was like, oh yes, this is something that would be cool to play around with. And I actually missed Gary's talk because I think I was out of town at the time. And so Jen was like, well, this was amazing and we should meet this person. And then Scott who's going to talk last, but Scott had the idea for this project and was like, you seem like you might be interested. And I was like, yes, I definitely want to do this. And I also, since Jen brought up that Gary is working on sonification, one of the goals of this project that hasn't been coded yet because these things take time is to have the software that he's working on isn't something that can be really run through the web. And you have to bring the data to it and it has to come into it in specific format. So one of the things we want to add to our software is the ability to write out the configuration files for his star sound, so that it can be a through line to easily get data from MAST and then sonify it. And we're providing, Python sonification because that is a very popular language in astronomy. But we also, like, one of our goals as part of our accessibility goal is to be interoperable with the other projects that are out there, because there are a lot of different ways to sonify with a lot of different strengths and weaknesses depending on what specific task you're looking for.
All right, fantastic. Scott, how about you finish us up on this question?
I'll try and do the short version. There's a lot of other questions, but yeah, we go to an annual meeting every year, and I like to go up and down all the posters, and I stumbled across Kate's poster, Kate Meredith, who's in the chat, as well as Bill, our other two teammates. So great work on them. And I ran across a student who was giving this demo of showing how constellations could be shown on an umbrella with things stuck on the umbrella so that you could touch and feel the constellations for those who were blind. And you could spin the umbrella, which looks like a dome, and really get a sense of how the sky moves from touch. And that was just a fantastic conversation. So that combined, that was sort of started our working relationship with Kate and Glass Education. And then that combined with my dad did some volunteer work for the Lions Club, which is a volunteer organization here in the United States that has done a lot of work for people who are blind and low vision. And I guess I took on that sort of interest as well. But yeah, I want to make it clear to everybody, we are not the people who have invented sonification. People have been working on sonification for decades. But we're taking a lot of that work and trying to make it part of the archive. So yeah.
All right, fantastic. All right, so Grant Justice has been monitoring the chat more closely than any of us. And Grant, why don't you come join us and tell us the questions you found in the chat for the group?
Absolutely. First off, I would just like to say thank you to the audience because we had some great answers and some great interaction. All right, so the first question I have. So on one of the first graphs that you put up, I believe it was the very first sonification graph. What is the explanation for the decreasing slope of the relative lower values of oscillating star brightness?
Yeah, I'll take a stab at that one first. So I think the person there noticed that in addition to the pattern, there was a sort of trend as well. And I don't have a direct answer for that, but the one thing to point out was it was zoomed in. And so if we zoomed out the full light curve, which if it's Kepler or TESS, they observe the targets every half an hour for months at a time, continuously. And so you could actually see a better pattern. Now, whether that undulating pattern is something real going on with the star itself, which it might be, or sort of some calibration that wasn't perfectly done, we'd have to investigate. But I do think there is an undulating pattern that you saw, even in the zoomed in version. Whether that's sort of not perfect calibration or something real, we'd have to do some real science behind it. But that was a good observation. And many times those patterns are real, and they tell us something about the physics happening.
Right, and
Wait, so
go
can
ahead.
I just interject? Are we talking about the first light curve on the game show?
No, it was the part of the first talk. The very first one you guys put up. when we were still explaining. But Scott answered the majority of what
Okay,
it
because I
was.
was gonna say I know at least like the Kepler 12b one and the some of the other transits. It is instrumental because I've worked with those specific light curves, and there is an artificial trend that the Kepler data has that typically, and I left it in intentionally because that's something that you have to deal with as an astronomer, determining whether or not it's real. And in this case, it's an artifact of the instrument.
Cool.
That's actually leading me to the second one, which was, does the longer scale variation show this as well, which is what Scott just elaborated on before we got there. So next up, who/when did astrosonification come about? Because we use sonification in a lot of different methods, but astrosonification.
That is a good question. Actually, probably Kate, if Kate's still in the chat, would know the best, but I want to say it's been around since at least the mid-90s. I think there's a pretty seminal paper, not necessarily about astronomy, but other types of data from, I think, like 1997 or something like that, if I'm not mistaken. And I know for a fact over the last 10 or even more years, there have been individuals working very hard in ways of representing not just light curves like we've shown, but also people are doing work to sonify images, if you can believe it or not. And they have some really good solutions for that, as well as other types of data. So it's a small but growing field. And one of the things we're trying to do with other groups around the world interested in sonification, of which I saw at least a couple in the chat as well, is to work together to try and pool our resources together.
Yeah, Scott says, like when you showed that, you can feel the motion of the sine wave with the sound and everything. People have created several sonifications in astronomy where you take your mouse and move it across the image, and the sound changes as you go across different things to indicate certain things, like the Hubble Ultra Deep Field. Each galaxy that you come across has a different tone based upon the redshift of that galaxy, for example. So, doing images as well as light curves, quite a variety of possibilities.
So you mentioned them moving the mouse across the screen. I know of some blind astronomers who use touchpads and some ways of physically interacting with a piece of hardware that they could actually feel where they're moving, and then the sound gives feedback as they run their hand over a certain area. And then also similarly using kind of DJ kits and interacting with the sonifications and updating them with this like physical interface.
Cool.
That's so cool.
What's up, Grant? What's next?
All right, so next one is kind of a continuation as well. What else do we use sonification for? I think more specifically in science, but just as a general, like an idea of the usage for the audience. I know
so
for a fact,
many things.
Oh,
Sorry, go ahead.
Oh, I was going to say, from my experience, I know that it's used in testing for like pressure cracks in nuclear reactors and quite a bit of manufacturing as well.
Yeah, I actually went and did, I don't know, not like a survey, but I did just Googling around to see what else is out there. And there's a lot of different things. There was something that was, I guess this isn't directly in science, but it was really cool. It was sonifying to look at the population density based on subway stop in Manhattan. And so the way it mapped through is that it was like you took a train line and it would, so there was a easy way, right? Because people are familiar with what the subway system looks like in Manhattan, and so that would take you through, and it would change with what I remember was population density, but I think you could also change it and have like average numbers of different things, which was very cool. There's some sonifications with earthquakes detection as well. It comes up in a lot of places.
I think it's worth mentioning too that there's sonifications in just everyday objects that you use, and you just probably haven't thought of it as sonification. So, I mean, the heartbeat star we showed is based on an EKG machine, but an EKG machine is a perfect example of sonification being used in the medical field that you've definitely, well, you probably heard before. So lots of examples like that. Once you start looking for it, you'll see it. I mean, even your microwave counting down the number of seconds and ringing is some form of sonification, I think.
Well, I think we're all used to hearing a pot bubbling, right?
Yeah.
You're not paying attention, but you're hearing the pot bubbling on the stove, and you go, "Oh, time to go, take care of the pasta or whatever."
Or when the teapot wails.
Yes, exactly. That's a great one.
Or just pouring a glass of water, you hear it, the sound get higher pitched as you near the top. That's one a blind friend of mine pointed out to me that I'd never thought about, but you can absolutely do a lot of things, and the visualization makes it much more accessible as well, which is awesome. Or the sonification, rather.
Well, and this is also the distinction that Scott was talking about at the very beginning. The tea kettle wailing could be a sonification. The water is boiling and that's making a sound happen, but hearing the water boiling, that's not a sonification, that's a sound. Hearing the water pouring, that's a sound. So these lines between sonification and sounds can be, especially when you get to a sound that is a real sound but isn't actually audible to the human ear, being moved into a range that the human ear can hear it, because it's a sound, but you wouldn't have been able to hear it without this additional sonification component.
Such as the black hole merging the chirp, right? Yeah.
Yep, that's a perfect example. Yep. And the EKG is great too, because it's representing heartbeats as sound. It's not actually listening to sounds that the heart makes. Yeah.
Right. So
Awesome.
Question that I know some of our audience has is this going to move from doing sort of public outreach and getting people to understand and appreciate it to actually doing research? So will we ever have Jodie Foster sitting out with her headphones on, listening to the sounds of the star, listening to the radio signals, and actually doing analysis, which of course never could happen but for many different reasons. But what do you guys think?
Yeah, I love contact. That's a great question, and we have that now. So one important point of the project is our goal is to make sonification that is useful for research purposes. A lot of people make sonification for things like press releases or presentations or art exhibits, and they really massage and change the sound to be, a certain representation that works well for their particular case. But our software is designed to enable real research, guts and everything. So if it sounds ugly because the data is ugly, we need to make sure that's maintained. And we are also, this is a very important point, we are working one-on-one with many blind and low vision participants who are testing and giving us feedback on our project. So we do have, several blind, low vision, astronomy students, physics students, computer science students from around the world working with us to make sure that this is not only a good portrayal of research data, but also something that's useful for them, because that's ultimately what this is for, not for us.
That was something that came up very clearly through some of the usability testing I've been doing. But one person in particular who I think had studied science in college, but ended up not being able to enter the field because she was blind and there's just too many barriers for her. So she wasn't able to pursue it as a career, unfortunately. And so when I was going through this usability testing with her, and then at first she didn't realize, she was thinking it was these massaged outreach style sonifications. But when she realized that this was software that she would be able to use to generate the sonifications herself, she was so excited, because that means you can do research. If you're listening to something someone's already massaged, that means that all the research has kind of been done, right? Like anything there is to know about that is probably known by the person who put that sonification out there. But the fact that we built this as software means that people can sonify their own data and study it and then do real research with it. So that is the thing to really focus on here. This is enabling research.
And one specific use that came up in another usability test that Jen did was with a current undergraduate who said that something that she'd been struggling with, she's working looking at actually light curve data like what we're using, was that they were running it through a pipeline process, you know, and doing their analysis on it. And she would do that. And then someone who is sighted would come in and look at the light curve and say, well, that light curve clearly has problems. And she couldn't tell. And she was like, well, with this, like, they wouldn't, she was like, well, if I could sonify it, then I could listen to it. And, you know, I would still have to go through the analysis. That's what the research is, but would be able to do that check that sighted researchers do, where you bring up the light curve and you look at it and you go, oh, well, that's clearly garbage because it just doesn't look real, you know, and that wasn't accessible to her. But you would be able to hear that because it would just sound weird and different, and so that, you know, is maybe not as exciting as Jodie Foster being like, oh, I've discovered aliens, but that's an important use case because it's these mundane things that make everyday research harder. Is like when you realize you just spent an hour running a, you know, piece of data through a pipeline that's useless because the data was bad to begin with. I mean, we all do that when we have everything at our fingertips. Imagine how often you do that when you're missing the ability to just scan it.
And do you guys have any ideas of possibly, you know, citizen science sourcing it for these huge data sets that might need to be sonified? That because it sounds like you could train the public to listen for certain things and identify, you know, because, you know, citizen science is great for looking for those needles in a haystack. And if you can train people, you have any thoughts on that front?
Yeah, one of the projects in the back of my mind is to make a test.radio. I don't know if people would be interested in it, but I've been thinking about, well, we can maybe make a Spotify channel that just plays all these light curves. So I'm actually working today on preparing to release something like 19 million light curves from the test mission, 19 million stars, and no one ever will be able to look at them or listen to them. But maybe if we all listen to some while we're working or in the car or taking a shower or whatever, we might be able to make some really cool discoveries. So yeah, there's people. There are also other groups looking at Zooniverse. But a lot of our audience might be familiar with Zooniverse. There's at least 1 or 2 groups looking to incorporate sound as a Zooniverse project, and we could do the same thing as well if there's interest and resources to do so. Yeah, we really want to engage the public. And also, I think there was a question about being able to contribute if you know software. This is open source, so if you really want to get interested on a volunteer basis and you know how to code, it's open source. You can do a pull request. We're open for business, as it were, but without the business part.
We're open for science.
We're open for science and contribution and collaboration. That's what it's all about.
Okay. Clara, there was a question that sort of asked about what would programming skills do I need to do astronomy? And I've actually gotten that question a lot from when I give career talks for those. So those who, you know, want to do astronomy stuff, you're doing Python. Can you just give an idea of what people would want to study in terms of the programming languages and why?
Yeah, I mean, so if you want to get into astronomy, definitely Python is a great place to start. I mean, I recommend people interested to get into, I recommend that people start with Python when they're starting with programming languages. And I recommend this for basically one very important reason, which is that it is an incredibly popular language and there is an abundance of information about doing things in Python on the internet. I noticed this very much. I'm a Python programmer and I'm a C programmer, and I'm very good at both of those languages, and I can easily get myself into a situation in C where I've hit a problem and I go to the internet and I can't find anything and I just have to sort of bust my way through it. And I'm experienced enough now that I can do it. But I've almost never got myself in that situation with Python. Even with the really weird, complicated things, there's someone else who has done it and who has put it on the internet. And that makes learning it a incredibly more rewarding experience. And then the other thing for astronomy, particularly if you're not currently in school, in a traditional physics program with a lot of people around you, is there is a nice astronomical community built around software. If you're interested in getting into things, I recommend checking out Astropy. It's the main Python package for astronomy. But more than that, it is also an ecosystem. It's a great community. They run community events. They run hack days. They run hackathons, some of which they run workshops that are really invested, and they're really invested in bringing people into the community. They have an extensive tagging system on their issues, so you can look for things that are easy. They have a whole Astropy Learn network that helps you learn how to use Astropy, but it can also teach you a lot about astronomy. I have an undergraduate degree in astronomy, and now I have more experience in astronomy. But when I started working at Space Telescope, my Python abilities outstripped my astronomy abilities. And so I would go to these tutorials and yeah, they're teaching me how to manipulate tables and how to use this particular Astropy package, but that wasn't really the hard part for me. They were also teaching me, how to analyze a star, how to analyze a spectra, how to do all these different things. So I think that's a really great place to start. There are other languages that are useful for astronomy, but the barrier to entry is lower for Python, and you'll get to interact with astronomers basically as soon as you want to.
And that's a great point about the software ecosystem that enables science. There's so much, more than just, everyone thinks of astronomers looking at using the telescope and getting data. There's such an amazing ecosystem of other things that have to happen to make science happen.
And there are lots of
Oh,
Python tutorials out there that use actual astronomical data from those telescopes. So it can also be a quick way to get to see the same data that all of the astronomers are looking at.
All right, we're getting close to 9:30. Grant, is there any one last question, or do you think we're done here?
we are through the questions that the
Great.
chat asked.
All right.
And yeah, I just think, Scott, if you wouldn't mind just dropping some of the links, or because there's some people asking about Astropy and whatnot.
Oh yeah, I will
remember that there are, like, for this lecture, there are thousands of people all over the world doing this sort of stuff, and they would love nothing more than for you to help explore space with them. Like, become a part of something awesome.
Yeah, and
it's science, so like there's no upfront, there's no getting into it. You just find some cool people and
yeah, I encourage everyone to sign up for our mailing list. We also have the Astronify homepage, which I will link in the chat as well. Has all of our contact info. We have a mailing list. We have a email that you can send to our group. I'm on Twitter, which are on the front page there. Get in touch. We want to reach out to everybody and do our best to work together. This is not a secret project. This is open for everyone to be able to benefit from, especially people who are blind and low vision, but also everyone else too. It's just a lot of fun, and it's really cool.
All right, Jen, did you have anything to add before we go?
No, just go to our website. Join us.
I've got one thing to add, which is if you are watching this recorded, please still answer the survey. These guys are still like keeping track of it, and it helps them out. So
yeah, every survey response that you get, I will get an email, and I will be checking it, and potentially will be, it'll be impacting work going forward, and maybe we'll even be writing some papers with it in the future. So really appreciate it.
All right. Well, Jen, Scott, and Clara, thank you very much. We really appreciated this wonderful talk. To our audience, December 1st will be the next public lecture series, Shaping Galaxies with Supermassive Black Holes, Mitchell Rovalsky. We'll see you then. Thank you, and have a great day.
Good night, everyone.